Hi friends, I'm Sridhar and I'm doing this video on connected motion of bodies, and in the process of doing that we'll also try to understand what are free body diagrams. I'm taking an example of two bodies placed on an inclined plane, and we will look at the connected motion of these two bodies m1 and of masses m1 and m2, and we'll also look at the free body diagrams. Before we do that, a little bit of background, right? First thing is, let us see what happens when we have an object on an inclined plane. Let us say we have an object right on a table, right, and let us say the mass of this body is m. So force mg acts in the downward direction, and there is a normal reaction in the upward direction, right? So this is the reaction to the force mg, and r is equal to mg, right? This is a simple case we have discussed earlier. Let us see what happens when this object is placed on an inclined plane, right? So let us say this is inclined plane on which we're keeping the same object, right? So I keep the same object on inclined plane, right? And let us say this is of mass m, right? In this case, right, there's a force which is acting in the downward direction, which tries to take this mass in the downward direction along the inclined plane, and of course there is a normal reaction because of the weight acting in the downward direction. Mg acts in the downward direction, and this mg has two components, one which takes it in the downward direction and one is the normal reaction, right? This is the normal reaction to the force which is acting onto the inclined plane, and if I take this angle as theta, then we know that this force which tries to take it down is equal to mg sine theta, and the normal reaction r, right, is equal to mg cos theta, right? We have done this earlier. I thought I'll just quickly revise this, so that because we're going to use it in this problem. Okay, let's move ahead. So we are talking of an inclined plane. We have two objects m1 and m2 connected by a string, right? The angle of inclination of this inclined plane is theta, and a force F acts on this, right, through a string, right? So this force F is pulling these two in the upward direction. Let us say these two masses are moving up with an acceleration a. So this mass m1 is moving up with acceleration a, m2 is also moving up with acceleration a. Now what I want to find out is what will be this acceleration, right? I'm thinking that I would be aware of, or I would be given the values of m1, m2, f and theta, right? These four things I would know, right? And what I want to find out is the acceleration of this. Okay, when this force F acts on this, right, this string gets into a very taut condition, right? And there's tension in this string, right? And the tension is T. Let us say the tension is T. Now some of you must be wondering, how did this tension come into play, right? Okay, let me explain this, how this tension comes into play. Let me take a very simple example, right? Let us say there's a string attached over to a ceiling, maybe, right? There's a rope which is attached to a ceiling, right? Now in this condition the rope is not under tension, right? But when I attach a weight to this, right, let us say I attach some weight to it, this rope will come under tension, right? It will get pulled down, right? And that is because there are two forces which is coming into play. One, W acting in the downward direction, and this particular ceiling also applies a force in the upward direction. So there are two equal and opposite forces which get this rope into which generate tension into this rope, and this tension acts in the upward direction over here and downward direction over here, and this is how tension gets developed. For example, let me take the example of this wire. Right now this wire is not under tension. If I apply force on this wire in one direction, right, it is not under tension, but when I apply a force onto this in both directions, you can see that there's tension in the wire, right? So whenever any rope is pulled in both the directions, opposite directions, it comes under tension, and this T and T represent that tension. Okay, so we have tension T over here, and now let us look at free body diagram. In free body diagram, what we do is we take one object at a time and analyze all the forces acting on this, right? So let us begin by taking m1. So once again I'll draw the inclined plane, and I'll assume there's only one object m1 on this. So let us say this is the inclined plane, right? So this is the inclined plane, and let us say we have object mass m1 over here. Let us say this is m1. Now if I look at only m1, what are the forces acting on it, right? The one force I can very clearly see is tension T. So tension T is acting in this particular direction, right? Since it is on an inclined plane, m1 g sine theta will act in the downward direction, right? So this is m1 g sine theta acting in the downward direction, as we discussed over here, right? And the normal reaction, right, right? The normal reaction R, right? This R will be equal to m1g cos theta, right? Let me just draw a line over here so that R is equal to m1g cos theta, right? Also, I know that this particular mass m1 is moving up with an acceleration a. Now, we know that the net force acting on a body of mass m and moving with acceleration a is equal to m. So F net is equal to ma, right? We know that, right, by Newton's second law of motion. So if this particular mass m1 is moving up with an acceleration a, the net force on m1 will be equal to m1 into a, right? That would be the net force. Now, what are the various forces acting on this in the direction of motion? T is acting in the direction of motion, mg sin theta is acting opposite to the direction of motion. So the net force acting in the direction of motion is T minus mg sin theta, m1g sin theta. This is the net force. T is acting in this direction, which is taking it up. m1g sin theta is acting in the downward direction. It is trying to stop it from going up, or is trying to de-accelerate it. So the net force which takes it upwards is T minus m1g sin theta, and that is equal to m1a. So I get the first equation, right? Okay, what are the other forces which are acting on this object? R is acting on this object, the normal reaction, and R will be equal to mg cos theta. Right? This is so because there is no acceleration in the vertical direction. So mg cos theta, this is mg cos theta. Right? As we discussed over here, mg cos theta. So R is equal to mg cos theta. So this is one more equation I get for the mass m1, right? Okay, now let's look at mass m2, right? So I'm now looking at mass m2. So I'll again show mass m2. Let me draw an inclined plane. Okay, let us say this is mass m2. Now, if I look at mass m2, I'll keep this diagram for reference, right? So if I look at mass m2, F is acting in this direction and T is acting in this direction. So these are two forces acting, right? So one is I can show F acting in the direction this way and T acting in this direction. Apart from that, we will also have m2g sine theta acting in this direction, R, and this would be m2g cos theta. And we know that m2 is going up with acceleration here. So again, net force acting on m2 will be equal to m2a, right? And which are the forces which are acting in the direction of motion? F, T, and mg sin theta. And force F is the one responsible for taking it in the upward direction, right? And T and m2g sin theta, they are opposing that motion. So the net force acting on m2 will be F minus T minus m2g sin theta is equal to m2a, right? So this is one equation I get, and of course I get the equation. Now I'll, instead of calling this R, I'll call it R dash to differentiate between the R over here, right? The R over here, and so I'll call this as R dash. So R dash is equal to m2g cos theta. Okay, so I have got equation number 1. Right, I'll call this equation 2, I'll call equation 3, and let us call equation. So I got 4 equations, right? Now, if I look at all these equations, and particularly if I let me focus on equation 1 and 3. So let me write down equation 1 and 3 again. So T minus m1g sin theta is equal to m1a, and F minus T minus m2g sin theta is equal to m2a. Now, if I look at these two equations closely, let me identify in this which are the terms which are known, right? I know which of these terms. So I'll underline the terms which I know. I know m1 is known, g is known, sin theta is known, m1 is known. So T and A, I don't know T and A. In this case, F is known, T is not known, m2 is known, g is known, sin theta is known, m2 is known. So T and A are not known. So I have got two equations, right? These two equations, and there are two unknowns there are two unknowns, T and A. So if I solve these two equations, I can find out the value of find value of A and right. So this is how I would look at a problem on connected motion of two objects which are on an inclined plane. So I look at each of them individually, look at various forces, get equations, and then find out A and T. So now everything about the object's motion is known. I know with what acceleration it is going up. I also am aware of what is the tension in the string. The knowledge of tension in the string is required so that you are able to design this string, right? Depending upon the tension in the string, expected tension in the string, you can design the material and the wire of this particular string. So we need to know the value of T and we need to know the acceleration A. Okay. With this, I have just about completed the discussion on connected motion body for two objects on an inclined plane. Of course, we have two more equations which we have not talked about. R is equal to mg cos theta, sorry, it should be m1g cos theta, and r dash is equal to m2g cos theta. Help us find out what is going to be the force acting on the inclined plane. Hope this has helped you understand the free body diagrams for connected motions of body, and in one more video I'll look at a few more examples of connected motions of body. Thank you.